Alright, let's look at this interesting formula called Euler's formula. Right? It goes something like this. E to the I theta is equal to cosine of theta plus I sine of theta. So we are plugging in the complex number into the exponential function, and which can be written this way. Right? So what we're going to do is we want to prove this using power series. Right? So I already wrote down the useful power series. So for e to the x is a summation from 0 to infinity, x to the n over n factorial. If you write this guy out, it's going to look like this. It's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. And you can see the pattern, so I'll just say dot dot dot. Alright, and for cosine, so cosine is an even function, and it's going up and down, so it's an alternating function, and it goes kind of something like this. It's going to be 1 minus x squared over 2 factorial, then plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. Right? Then sine is the one with alternating, and also picks out all the odd powered terms. So it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Alright, so keep those guys in mind. Alright, so let's prove Euler's formula. So here's the proof. Alright, so let's start with e to the I theta. Alright, so since we know that e to the x can be written as this power series, we can just replace x by I theta. So it's going to be 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial, and maybe one more, plus I theta to the 5th over 5 factorial, and so on. Right? So let's simplify this. Right? So if you have, let's see, one's clean enough, and I theta, I like it like that. Alright, so you have I theta square. I square would be -1. Then you have the theta square, so it's going to be minus theta squared over 2 factorial. Right? So here, this is going to be I cubed. I cubed is going to be, let's see, I times I is -1 times I. So it's going to be negative I. Then you have a theta cubed over 3 factorial. Alright, I to the 4th is going to be +1, so it's going to be just plus theta to the 4th over 4 factorial. Alright, so I theta to the 5th, I to the 4th is 1, so it's going to be just simply I. Then you have a theta to the 5th over 5 factorial. Alright, and so on. Alright, then you can see that here, if you pick out all the ones without I, so let's see, this guy right here, and this guy doesn't have I, and this guy doesn't have I. So we have these terms. So this is going to be right? So this is the real term. So you have 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial and a minus and so on. All right. Then let's collect all the one with I. So the rest of it has I. So I'm going to put the I out. So you have a theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus and so on. All right. Then you can see that we recognize these terms. You can see that 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial. This fits the pattern of cosine, except that the x is replaced by theta. So you can see that this guy is going to be equal to cosine of theta plus I. All right, and again, we recognize these guys, which is comes from the sine function, just that we replace x by theta. So this is going to be I sine theta. All right, so that's how you establish Euler's formula, and we can use our power series for e to the x, cosine of x, and sine of x. And it's kind of strange to have a complex number inside a complex exponential function, but we can still make sense, and e to the I theta is identical to cosine of theta, which is the real part, plus I sine theta, so sine theta is the imaginary part. Alright, that's it. I hope that this was clear.